So let me introduce our speaker, Professor Admir Greljo from University of Bern. He received PhD from University of Ljubljana at 2014. After that, he experienced a postdoctoral researcher at University of Zurich until 2017 and the Johannes Gutenberg University of Mainz until 2018 and a senior research fellow at SAN until 2020. After that, he has been SNSF Excellenza Professor of University of Bern. He is doing researches on a broad range of high-energy physics phenomenology. Today, he is going to talk about model building and phenomenology with leptoquarks. Professor Greljo, please start. Thank you very much.
Thank you very much for the invitation. It's my great pleasure to be virtually, at least, visit your group. I hope at some point also come in person. So I want to talk about leptoquarks, so model building and phenomenology with leptoquarks. So leptoquarks have been a very popular topic in high energy physics phenomenology in recent years. So here you can see the citation record from the INSPIRE search, looking for papers that have a leptoquark in their title, and you can see a steep rise of these entries, starting somewhere from 2014 to 2015 and so on. Actually, back then in 2016, we wrote a review paper, so published in Physics Reports, on physics of leptoquarks in precision experiments and particle colliders. And you can imagine that by now this report is rather outdated, given so many references in recent years. So my plan today is to talk about few of my own recent papers on the subject. And I apologize in advance because perhaps it might be incoherent, and I will try to make a break and so on. And please interrupt me at any point if you have questions. All right. So what is a leptoquark? So we define a leptoquark by this dimension 4 local interaction, where this new field, the leptoquark field, couples directly quarks to leptons. And from this definition, it follows that leptoquarks are colored triplets, since they have to annihilate the quark color. They are spin 0, we consider spin 0 and spin 1 particles, so either scalars or vectors. And they are electroweak singlets, doublets, and triplets. This comes because quarks and leptons are either singlets or doublets. So a trivial or fundamental representation. And also, when we decompose the electroweak components, we get the electric charge, so the charge under quantum electrodynamics, to be either plus minus 1/3, plus minus 2/3, plus minus 4/3, and plus minus 5/3. So over here you can find a table. Sorry, what's happening? You can still see my slides, right?
Yes.
Okay, very good. So you can see the table of all the leptoquark representations with their names written on the here. So we have scalars and vectors, and in these different representations, where the first number is the QCD color, the weak, the SU2 weak, and the hypercharge. So what's the motivation behind studying leptoquarks? So from the theoretical point of view, it's the idea of quark-lepton unification. We observe a very peculiar charges, so the hypercharge of the standard model fermions. So in particular, we do not understand why the hypercharge is quantized, and why in particular we have, for example, it boils down to a question why the hydrogen atom is neutral, why the electron has exactly opposite charge to the proton. So in the standard model, we have anomaly cancellation, but this is only a consistency condition on a theory that to many authors means that hints at some kind of underlying unification of quarks and leptons, that we put these fields into a multiplet of some semi-simple group. And in those kind of cases, in those scenarios, leptoquark would naturally arise. So whenever we talk about quark-lepton unification, we would have naturally leptoquarks. So therefore, they're present in plenty of beyond the standard model scenarios. For example, Pati-Salam, where the first leptoquark was introduced, and the variations of the Pati-Salam. The good thing about Pati-Salam that it can be relatively light in such a way that it can be interesting for the phenomenology, besides the usual proton decay and things. Then, of course, we've got SU5, SO10 grand unification. Leptoquarks, interestingly, are basically the squarks in R parity violating supersymmetry. So when we are talking about RPV SUSY, then effectively we are talking about leptoquarks. And then they could also come up in extended composite Higgs models, where, for example, leptoquarks could come together with the Higgs to be the pions of some new strong dynamics, etc. So there are plenty of reasons to talk about leptoquarks and to study them in phenomenology. However, what is driving this recent interest that I showed in the INSPIRE track record is the phenomenology. So there have been certain anomalies reported in experimental measurements that I'm pretty sure you've started look at these things already, and this happen in B meson decays, and also, for example, in the anomalous magnetic moment of the muon. So in this talk, I will focus. I'll dedicate some of my time to discussing the first two of these flavor anomalies. So the first one is a rare decay of a B to a strange, and then lepton anti-lepton, and the other one is the anomalous magnetic moment. So leptoquarks turn out to have very desirable properties to address these flavor anomalies. So in particular, they give semi-leptonic transitions, so quarks going to leptons at 3 levels. So you can imagine attaching another quark and lepton here, and you will get a 3-level diagram for quarks going to leptons, a semi-leptonic transition. However, if you want to generate 4 quark or 4 lepton transitions, so things like meson mixing or charged lepton flavor violation in a lepton going to 3 leptons, for instance, this is a loop suppressed process. So one has to close the box diagram in order to generate these transitions. And in those transitions, we haven't observed any anomalies so far. And finally, for the G-2 of the muon, it can give a chirality enhanced contribution. Certain types of leptoquarks could have a chirality enhanced contribution to the anomalous magnetic moment of the muon. So this whole hype about leptoquarks in recent years was mainly driven by these experimental anomalies in B physics and the anomalous magnetic moment of the muon. So this talk will not be, unfortunately, I will not discuss the experimental aspects of these anomalies. I want to focus on the theoretical issues and some theoretical strategies that we discuss when facing this problem. So the starting point of the discussion is about the accidental symmetries of the standard model. So what these things are. So let me start with trying to explain them. And as we already know, they are very important for the phenomenology. They have important phenomenological implications. So if we consider the standard model Lagrangian, which without the Yukawa interactions, then there is a huge global symmetry of the kinetic term. So we've got 5 gauge representations of the fermions, all of which come in 3 copies. 3 flavors. And so we've got a U3 group for each of the species of the gauge representations. And now when we introduce Yukawa interactions, we can use this freedom of U3 to the 5 transformation and also a singular value decomposition theorem to go to a basis where these y hat quantities are diagonal with actually real non-negative entries on the diagonal and will be identified with the fermionic masses. And V is the unitary matrix. It's a unitary matrix known as the CKM mixing matrix. So you can see from this expression that all quark flavors are broken down to the universal U1, which is the baryon number. However, the lepton flavors, they actually so the lepton flavors, they are actually individually preserved. So there is a U1 for each of the lepton flavors, electron, muon, and tau. So in the standard model at the perturbative level, neglecting the neutrino masses for the moment, just the standard model with these 5 representations and considering only the renormalizable Lagrangian, has a baryon number times the individual lepton number. So lepton flavor is conserved. The 3 combination of these gauge groups, so B minus L, and the difference between the lepton flavors are exact, meaning that they don't have quantum anomalies, while B plus R is anomalous. And the physical effects of these are the non-perturbative spaleron dynamics, which is not very important when we talk about zero temperature quantum field theory. So they change the implied selection rule, so that is they change baryon lepton number by 3 units. Okay, so these are the short review of the accidental symmetries in the standard model. And what we know very well about extending the standard model at the TeV-scale, very close to the electroweak scale, then there is this rule that is imposed to us by data, by experiment, that a viable model at the TeV-scale should not excessively violate the accidental symmetries. And this is not a generic case. So if we think of some generic beyond the standard model, we at the TeV-scale, we typically get a violation of these accidental symmetries. Example is leptoquarks. So if you introduce a leptoquark field S, can you see me pointing at things on my slides?
Yes, it is around the S.
Okay, thank you very much. So the S is a leptoquark field, some scalar leptoquark. In general, at dimension 4, a renormalizable interaction, we can write an interaction between a quark and a lepton, from which we can assign a baryon number to the leptoquark. But typically, the gauge symmetry allows to write another interaction between a leptoquark with 2 quarks, where the baryon number would be different. Meaning, if both of these terms are present, we are breaking baryon number. And in particular, the proton decay constraints, simply experiment saying that proton lifetime should be much bigger than 10 to 34, should be very large, would imply a very stringent limit on such a leptoquark. So if we assume order 1 couplings, then these leptoquarks should be close to the gut scale, very, very far above the TeV scale. In addition, if you look at the...
So I have a very naive question. I mean, maybe
Yes.
stupid questions. So the leptoquark can interact with, can couple 1 quark and lepton at the first, as shown in the first term. And the second term is like a QQ, but is it allowed to LL as well?
So it cannot couple to LL because leptoquark carry color.
Carry color. Oh, so okay, I see.
So they are
okay.
charged under QCD.
Okay.
This would not be gauge invariant operator. Okay.
So okay, so 2 color or 3 color can, I mean,
exactly. So here we have the Q. Yes, Q and S, we have 3 times 3 bar, and here we have 3, 3, 3.
Right.
So this is a singlet, just like mesons and baryons.
Right. Okay. Thank you.
Sure. When we introduce leptoquarks, we also break lepton flavor. So usually gauge symmetry tells us that this Y is a generic matrix. It's a complex 3x3 matrix, and in general we would have I and J could be we could have off-diagonal terms, etc. For a generic matrix, we expect to violate a lepton flavor down to the in this case down to the universal one, the total lepton number. And in particular, there are stringent constraints from charged lepton flavor violations, so mu to E gamma. For instance, where the branching ratio limit is at the incredible level of 10 to minus 13, and this would set constraints. This would translate on the bounds on the leptoquark. So a generic TeV-scale leptoquark with all these couplings switched and having like order 1 values is dead by precision physics. Okay. So another example of this instance is G minus 2. So this argument over here is a bit more general than the leptoquark, but it also applies to the leptoquark. So here I'm looking at this diagram where I want to generate a dipole interaction, which can be done by the leptoquark, as you can see over here. So leptoquark with a quark running in the loop. For example, a top quark would give a mass chirality enhancement. But in general, if I have indices, if I have general couplings like not diagonal, for instance, but just generic, then I can connect the anomalous magnetic moments to the radiative lepton decay. So for instance, one can connect delta A mu to a decay of mu to E gamma through the mixing parameter theta 1, 2. So this would be a mixing between the first and the second lepton generation. And the same can be done for tau 2 mu gamma. So here I'm normalizing to the upper limit of the branching ratio. And this is the measurement, the current combination of the measurement. So the discrepancy between the theory and the experiment for the anomalous magnetic moment of them. So in order to pass the bound from radiative lepton decay, the mixing angle has to be very small. So in the case of mu to E gamma, it has to be less than 10 to minus 5, and in the case of tau to mu gamma, less than 10 to minus 2. A naive BSM expectation is actually just would simply be something like this, the square root of the mass ratio, which is much bigger than these bounds. So what we learn from here is that we need sort of nearly exact lepton flavor conservation. Okay, this kind of discussion led us to consider a certain class of models, in particular where we gauge combinations of lepton flavors. So there will be extending standard model and considering leptoquarks within these frameworks. So putting leptoquarks within these frameworks of a gauged flavor, gauged lepton flavor. So this would be new type of gauge interactions that distinguish between electrons, muons, and taus. So the storyline in the first part will be that there will be selection rules that are implied on TeV-scale leptoquarks. They will not have generic interactions, but there will be important selection rules that will actually allow us to have consistent theory and to have a good description of the current flavor anomalies. All right, so here is a model that we studied. So the first version of the model was done in this reference over here with the postdocs in the University of Bern, Peter Stangl and Anne Seller-Thompson. And then we have generalized this together with Joe Davigi from Zurich. So the generalization is to charge a combination of the baryon number minus the lepton number and this combination of lepton flavors. So 2 times the muon number minus the electron number minus the tau number. So charging these combination, we are also introducing right-handed neutrinos, as you will see. will be free of anomalies, of quantum anomalies. So this will be a consistent theory. M and N are some co-prime integers. So their greatest common divisor is set to 1. So these are the charges for different fields over here. So quarks, they just carry a baryon number. Electrons and taus, they have the same charge, as you can see over here, n minus 3m. Muons have a different charge in terms of n and m. And the Higgs has no charge under the U1x. There will be some extra scalars, which are standard model gauge singlets, so phi e tau and phi mu. So they do not carry charge under the standard model gauge group, but they have a charge under U1x. So their role will be to spontaneously break U1x at some high energy scale and to give the mass to the new gauge boson. And also, as you will see, their charges are chosen by neutrino physics. So in order to realize neutrino masses and mixings. And finally, leptoquarks. So we add here 2 leptoquarks. So with these quantum numbers, so they are either weak triplets or singlets. So S3 will be SU2 triplet, and S1 is SU2 singlet. And they would have this charge, 2m plus 2m. So how is this charge chosen? So this charge, it's under the new U1 gauge group, is chosen in such a way that leptoquark can interact with a muon and a quark. So now we have an interaction. Gauge symmetry allows for an interaction between a leptoquark to a muon and a quark. However, since electrons and taus have different charge from the muon, we cannot write a renormalizable interaction with electrons and taus. And also, it turns out that the gauge symmetry forbids to write an interaction with the 2 quarks. This new U1x flavor, lepton flavor non-universal gauge symmetry doesn't allow to have this interaction simply because quarks and S have certain charge assignments which forbid it. It's a gauge symmetry. So in fact, it turns out that the leptoquark Lagrangian has an accidental symmetry, which is the one of the standard model. So U1b, U1e, U1 mu, U1 tau, where the leptoquark carries a baryon number and the muon number. So we call it a muoquark. Okay. That's the name, muoquark. So with this allowed interaction, we can exchange a leptoquark to give us quark interactions to muons. And we can also have contributions by this S3, the triplet one. And the singlet one can give us the correction to the anomalous magnetic moment of the muon. But we do not have diagrams to give for proton decay or for charged lepton flavor violation. These diagrams are not there. So that was the main logic. And then we did a comprehensive study where we looked into plenty of low energy physics observables that include electroweak precision test, flavor physics observables, lepton flavor violation, lepton flavor causality violation, anomalous magnetic moments, neutral meson mixing, semi-leptonic and rare decays, etc. So this we did within the context of the Flavio package, which is a global framework to do phenomenological fits, which is interfaced with this, so there's a smelly package that can build a global likelihood to analyze plenty of observables. So here we have something like 399 observables. So this is the starting Lagrangian. So here you can see that we have interactions between the triplet with we are interacting with the left-handed quarks and leptons. And here, this index 2 tells us that we have only interaction with the muons. Okay. Now we have, besides the masses of the leptoquarks, we also have these couplings eta, and these are basically, they carry one index, which is the quark index. So here we are considering the case where the largest of these couplings is actually with the 3rd generation of fermions. So this is motivated by the structure of the quark Yukawa, of the quark Yukawas, of the up and down quark Yukawas. So if these eta admit similar flavor symmetry structure as the quark Yukawas, that would mean that the largest coupling is to the third generation of fermions, and then the couplings to the light generations are related to the CKM element. So basically a transition from a third generation to the light generations, VTD and VTS. And so this is just an assumption in order to reduce 3 parameters to effectively 1 parameter. So this is 1 parameter, the overall eta 3, so the coupling to the third generation. And so here you can see the results of the fit. So this is the best fit region. On the horizontal axis, I have the coupling to the triplet S3, which gives us a 3-level contribution to B to S mu mu. And you can see that if the value of this S3 coupling is around 0.4, so it can reconcile the data, we can explain the effect. Here I'm choosing the mass of the leptoquark to be 3 TeV. So if I choose, for example, 6 TeV, this would mean that I just multiply these couplings by 2. So the ratio of the mass over the coupling is constant from the fit, because this is just an effective interaction. So 3 is just a choice. I could have used 6, and then this would be 0.8, and this would be 0.25 or so. So 3 TeV is above the collider constraints from the current collider constraints from pair production. So leptoquarks are colored and they are looked for at the LHC, and the current bounds are about 1.4, 1.7 TeV. So here you can see that we really have like very sort of very weak coupling. So these Yukawa couplings are rather small. In particular, you can you have a like delta chi-square difference from the standard model, which is 62, which is huge, and you can extrapolate these. You can run up these couplings, and there will be no Landau poles up to the Planck scale. These are very small, rather small couplings. Okay. All right. So that's it. Are there any questions about this this point so far? Because I'm moving to a different topic.
So you considered that the gauged leptoquark because the normal leptoquark does not meet the experimental condition. So my question is that leptoquark are colored. So I thought that they are naturally SU3 gauged, isn't it?
Yes, so leptoquarks, yes, they are charged under SU3 gauge symmetry, yes. However, the standard model symmetries are not enough, so we can write these interactions that break lepton flavor or give proton decay.
So in this case, we can think you added the another symmetry at U1X, right?
Yes, so it's an extra gauge symmetry, which in this case doesn't have. It could have phenomenological implications, but it not necessarily need to, because the Z prime, if you take it, the mass very heavy, it's actually the follow-up talk. So yeah, so basically the next part of the talk is a bit more theoretical. So and it basically starts with this question: what happens with the Z prime, and where is the breaking of this gauge symmetry? So in particular, I talked about the lepton flavor conservation, but we know that in nature, which is true in the standard model, but we know that in nature, lepton flavor is not conserved. It's actually broken by the neutrino oscillations. So how do we put this into the framework? And where can we break the U1 gauge symmetry? So that's the next story, and it led us to some interesting, actually theoretical discoveries that I will try to explain.
Can I ask a question before you continue? So
Yes, please.
you started from a particular gauge group B minus 3 L mu, right?
Yes.
And then you generalize it.
Yes.
The linear combination of lepton numbers, etc. So in that generalization, do you have any improvement or something nicer than the previous simple model? Or is it the generalization?
It is just a generalization. So it's a larger set of almost infinite set of models that will carry the same property. You know, actually, there is even a generalization of this where it doesn't necessarily have to be 2 L mu minus. So it doesn't have to be that two of the leptons carried exactly the same charge. They could all be different. One can also do with this. So it's not like there is something special with muons. So one can even have them all different. But in that case, it becomes, is this the extra story of how do you do neutrino masses? Okay.
I see.
Okay, so this will be connected with the neutrino masses. So it's precisely this story over here. So if you impose this gauged lepton flavor U1, then there will be zeros in the Dirac mass term and in the Majorana mass term, right? So this is precisely why these extra fields, so the scalar field phi e tau and phi mu are introduced. So they have two roles. One is to break the symmetry and spontaneously break the symmetry and make the gauge boson massive. But the other role is to also populate densely enough the neutrino mass matrix. Actually, in the case of B minus 3L mu, one needs only a single scalar field. So it's a little bit more minimal because the rest are just the Majorana masses. Okay. With this generalization, one needs two scalar fields. And so in particular, this is the texture that comes out from the gauge symmetry. So the Majorana mass can be populated entirely, but for the 0,0 term. And the neutrino, the Dirac mass, will have this structure. So it will have zeros in these entries, cross entries with the muons. However, this structure is enough to accommodate for the present observation. So it can accommodate for neutrino oscillations data, the Planck limit on the sum of the neutrino masses, the absence of neutrinoless double beta decay. Actually, it is more general than the structures that have been studied in the literature, which is this, which is known to work. So there is this 2,0 minor structure D1R, which be switching off this element, so putting it to 0, and also the one over here. So switching off two elements would give us the structure that has that is predictive. So it gives a prediction to be tested in experiment, and it's okay with the present data. So we are a bit more general than that. So we can sort of break this this prediction, and the details are given in this very nice paper over here. Anyways, so the question is the following. So now I'm breaking the U1 gauge symmetry spontaneously by the scalar fields in order to give neutrino masses. So now the question is, can this breaking be at a very high energy scale? So can I decouple the Z prime? Why would I consider this? So this would be like a standard seesaw mechanism, which is motivated by trying to explain the gap between the masses of the charged fermions and neutrinos. So if we have a right-handed Majorana masses that are very heavy, then we would get the seesaw mechanism and explain this mass gap. And possibly it could also be motivated by the standard thermal leptogenesis scenarios at high energies. But then there is a question. So if U1x is broken at the very high energy scale, then at the TeV-scale where we have our leptoquarks, then we do not have any more this gauge symmetry. And then naively, we could write renormalizable interactions, which are the diquark and the lepton flavor violating, that would violate the accidental symmetry. Okay. since now we are considering the gauge group being broken at some very high energy scale, at the TeV-scale, we have leptoquarks, and we could think of writing these interactions. We are sort of losing this protection. So the question is, what happens? Do we get proton decay? Do we have charged lepton flavor violation? Okay, so this is where we looked into a bit more details. And the answer is that the protection will still be there. It will be exact for baryon number. So it will be exactly forbid proton decay, and it will be approximate for lepton flavor. And there will be a discrete subgroup of the U1, which will ensure this. So consider, so this is how the argument goes. So we have these two scalar fields that have certain charges under the U1 symmetry, which is fixed by the neutrino masses. And then this subgroup, so the cyclic subgroup ZK, is unbroken. So what is K? So K is the greatest common divisor between the two charges. And then if you do the U1 transformation with the element which is 2 pi over K, you will get 1, because K is the divisor of phi, and this will be 1. So this transformation, so this subgroup of, so ZK subgroup, the cyclic subgroup of U1, will not be broken. So the wave will be singlet. So the fields are singlet under gamma, and therefore this unbroken discrete subgroup will be acting. It will stay intact deep in the IR. So it will not be affected by electroweak symmetry breaking nor by QCD condensation. So it will stay exact deep in the IR, and it will be acting. It will act on matter non-trivially. So in fact, so there is this existence of this discrete subgroup, and in fact we can think of what happens with the diquark operator. So the operator between two quarks and a leptoquark under this discrete subgroup. So we worked out this basically number theory problem, where we found the classes of U1s. So the M and N, remember, were these two combinations of a baryon minus lepton number and the lepton flavor, the traceless sort of flavor generator, for which this operator is forbidden. So for these M and Ns that satisfy this relation, the operator is forbidden. The discrete symmetry is either Z9 or Z18 that comes out from this breaking. And in these cases, there will be no proton decay. What is interesting is that from this equation is that both B minus L and the lepton flavor are required. So here, both M and N have to be non-zero. So one has to have a linear combination of B minus L and this non-trivial lepton flavor for this to work. Okay. So in the standard B minus L, which is the U1 that comes from, let's say, SO10, there we can write a dimension 6 operator, which is QQQL, which is consistent with this gauge symmetry and is baryon number violating. But in the case of these U1s, this is gauge symmetry, this is not possible. So is there any questions about this slide? This could be probably the heaviest slide I have.
And I think I missed something. For pi is leptoquark, right?
So sorry, say it again.
So in this case, the pi is leptoquark, right?
Pi?
Yeah, the scalar pi is leptoquark.
So S is the leptoquark. No, phi are the fields that break U1. So they are singlets.
I see.
Pi get a web, a leptoquark doesn't. Okay. So yeah, how much time do I have left?
I think 1 hour for your talk, maybe 30 minutes for discussion. So yeah, we have a plenty
Okay,
of time.
so I can take it easy. I don't have to rush because I have a plan. Okay, very good. Okay, I mean, please let me know if you have any questions about this. So
so I have a question. So can we make a potential for the leptoquark, the S field? Is it how to say prohibited by some symmetry?
so we can write some of the interactions in the S in the potential will be forbidden by this by the symmetry. But for example, some other interactions cannot be forbidden. For example, the portal interaction. So there is always this interaction which is S dagger S, phi dagger phi, which can be written. It's always consistent with all gauge symmetries. So this is the portal, the sort of the portal type of interaction. However, these interactions do not break since they did not break baryon number or anything like that.
What about the coupling to Higgs field? It is allowed.
Yeah. So there will be also S dagger S, H dagger H. So there will be a couplings to the Higgs field of the scalar leptoquark. Yes.
So the leptoquark doesn't have the vacuum expectation, but it's just a kind of assumption. Or...
Right. That's correct. So when one studies the scalar potential, there is actually a large parameter space for which leptoquark does not get a web, and that is our assumption. Okay.
And also, if the coupling to the Higgs is allowed, is there any restriction from experiment? Or...
Yes, so there are constraints that come from the leptoquarks running in the loop for the gluon fusion or for the Higgs to gamma gamma, but these are rather weak constraints. So they allow for TeV-scale leptoquark with order 1 couplings to the Higgs, even with order 1 couplings to the Higgs. But there is no reason that these couplings are order 1. Okay. So these constraints are there. There are also constraints for electroweak precision and so on. Yeah. Okay.
Thank you.
All right. So here the idea is that quarks will have the charge under the discrete subgroup which remains unbroken in such a way that the diquark interaction is non-trivial. It's not a trivial representation, and therefore it's forbidden because this is an exact symmetry. And in particular, when one looks into if one thinks about scalar, so leptoquark being very heavy and integrating it out to get the standard model effective field theory, so we can make a discussion about like the higher order corrections to the standard model Lagrangian. I mentioned 6 operators that are baryon number violating and so on, and higher operators that would be generated, for instance, by integrating out a leptoquark, like the one that is discussed in the context of proton decay. We see that those kind of operators, so there we will not have an S field, but then we can do the counting based on the charges of the quark fields and lepton fields. We can realize that all of these operators are forbidden, and actually that there is a selection rule that the baryon number can only change by 3 units. Okay. So you can only build a very high dimensional operator like dimension 15 or something, where the baryon number can only change by 3 units. So delta B equals 0 mod 3. That's a rule. And therefore it means that proton is exactly stable because proton decay is delta B equal 1 process. So it's exactly stable to all orders in a standard model effective field theory. Okay. Which I think is an interesting mechanism, which leptoquark can also be decoupled from this story and just consider this at the level of the standard model effective field theory. Interestingly, also anti-neutron oscillations are forbidden. So a neutron converting into anti-neutron is a delta B equal 2 transitions, which is forbidden. But then the processes like the sphalerons, the analogous of the sphalerons, would be delta B equal 3 processes, which are allowed. And this is good because we might this is good for the baryogenesis and so on. And also, like, neither proton decay nor neutron anti-neutron oscillations have been observed so far, and they put bounds on, very stringent bounds on new physics. Okay, and what about charged lepton flavor violation? So here we've got this discrete symmetry, which is, however, lepton flavor universal. This had to be the case because otherwise we would not be able to do the PMNS mixing matrix. And indeed, if we consider higher dimensional operators in the U1X invariant theory, we are able to write, for example, dimension 6 operators that will give us interactions of the leptoquark with electrons and taus. And this would be suppressed by 1 over lambda squared. So some scale which generates these lepton flavor violation in the U1X invariant theory. And a modest scale separation is sufficient to suppress charged lepton flavor violation to a level compatible with current bounds. So if we consider the scale lambda to be, let's say, 2 orders of magnitude above the scale at which we break U1X symmetry, then this is sufficient to pass the stringent limit from mu to E gamma, for instance. So bottom line is that proton is exactly stable, and charged lepton flavor is an approximate symmetry. So the question which is interesting to ask about these extensions of the standard model by a lepton non-universal U1s is always about, it's interesting to think about the unification. So we started by saying that leptoquarks are motivated by non-abelian, sorry, not non-abelian, semi-simple, possible semi-simple extensions of the U1 factors in such a way to explain the quantization of the hypercharge, for instance. So it's interesting to think about these things. So we know in the standard cases, such as baryon minus the lepton number, we have a well-studied unification scenarios which go through the Patti-Salam or through the and all the way to the, let's say, SO10 unification. So the question is what happens in this case. So it turns out that there is a path forward. This is a tentative gauge flavor unification scenario. So at very low energies, at the TeV-scale, we've got these mu quarks. So we got the standard model plus this discrete symmetry. When we go to high energy, eventually we will restore the U1X gauge symmetry, and that's the scale of the right-handed neutrinos. So we've got the seesaw mechanism. And then we can unify the hypercharge and the U1X into this factor. So actually, SU3L is like it's the gauge lepton flavor group, non-abelian gauge lepton flavor group. And so SU2 right and B minus L, you can recognize from the left-right models. So together with this SU3 left, they could embed U1 hypercharge times U1X. And now this can be embedded into, so this can be further embedded. So the B minus L times U SU3 times the quark can be embedded into SU12. It's a unifying group of color and flavor. And then we will have SU2 left times SU2 right. So this would be something like, not quite, but something similar to sort of like flavored variation of the Patti-Salam. And interestingly enough, all 3 families of fermions fit into two representations, so which is 12,2 and 12,3. two for the left and the right fermions. Like in Pati-Salam, all quarks and leptons built into two representations. We admittedly we do not have a working model yet, so we are currently studying whether we can have to really specify the details of the different symmetry breaking steps, etc. To see if it's viable or not. But I think it's quite interesting that also for these flavor non-universal extensions, there at least seems to be a path forward when it comes to the unification. All right, that's it. That's the end of the second part. I have 2 more parts to go. Do you have any questions?
So for concerning the proton decay, the stability,
Yes.
the proton decay, you have identified discrete symmetries. Then, so can you then raise up the ion breaking scale being compatible with the proton decay, right?
Yes, exactly. Yep.
So then the idea is the breaking scale is arbitrary as far as
So we don't. So it should be the maximal one is the like 10 to 14, where the coupling, like in the type 1 seesaw mechanism, but it can be anywhere between it can be arbitrarily high, not extremely high, cannot be. Eventually there is perturbativity which stops the coupling, but that is the idea. So we introduced the U1X in order to protect the TeV-scale leptoquark, but then U1X, the breaking of the U1X gives us neutrino masses, and we want to therefore push the breaking very high in such a way to have the standard explanation of the seesaw mechanism, where the light neutrinos come from the heavy Majoranas. But then somehow we need to see what's happening with our protection mechanism for the leptoquarks, and it turns out that there is a discrete subgroup, because the charges of the scalar fields are fixed by the neutrino masses. So somehow there is the connection between neutrino physics so these charges are fixed by neutrino masses, and then it turns out that there is a discrete subgroup which forbids proton decay for certain classes of M and N that satisfy this equation. And B minus 3L mu is one of those.
I see. So then there's some constraint on the ratio of M and N somehow, because you can rescale the gauge coupling.
Yes, exactly. So we are choosing
the denominator.
We are choosing M and N to be co-primes. So this was this condition over here. So we are pushing that thing into the gauge coupling. So we are choosing them to be co-primes. So the greatest common divisor is 1. So there is this freedom that's correct.
But as far as this condition is satisfied, you are free to choose any value. Maybe you are imposing certain conditions.
So there are extra conditions. So M has to be 3A plus R. So it should be basically, so M mod 3 should be either 1 or 2. So it should not be divisible by 3. N is divisible by 3, but not by 9. And okay, A and B are arbitrary. So they are arbitrary integers. And this condition is just the same one that you mentioned, that the M and N should be co-primes. So when these are satisfied, then you have this property that the proton is exactly stable. And in particular, this was not noticed before because people didn't really study much these. So they either studied B minus L, universal, that is motivated from the standard unification scenarios, or perhaps maybe only lepton flavored factors. But to get this working, you need both m and n. From this equation, it comes that both m and n should be non-zero. So you really need both of these terms to get this mechanism working.
Okay. So I noticed here that A and B, they are different. If they are the same, then the n over m can, like if you take if you divide the charge x by 3m, you are getting the coefficient in the lepton charge n over 3m, which is kind of sorry. So I mean, okay. So if A equal to B, I think the coefficient in the lepton charge equal to 1. Like a B minus L minus lepton charge, for instance. But if so A and B, they don't have to be the same, right?
They don't have to be. They can be arbitrary. A and B can be arbitrary integers.
I see. Then they can be the same, or they can.
Yes, I think they can. So if you take them to be 0, you can still get so if let's say A and B are 0, and then let's say R is equal to 1, then M is equal to 1, and N is equal to 3. So this will be 3B minus, so it will be just the factor for the
Okay.
yeah. So that can also work. That's one of the
I see. Okay, thank you.
Sure. Sorry, there is a comment in the chat, or
yeah, she's leaving early. Yeah, Yusan, she's leaving early.
Okay.
Yeah.
Okay, very good. Yeah. So so I've got 2 parts. I don't know if I have time. Maybe. So how much time?
Maybe how much time do you need? This is the last part for your talk.
So there are 2 parts. I can speak either about one or the other, maybe. Or so the first part is about looking more into these gauged U1, flavor U1 from the point of view of anomaly cancellation conditions, and making a catalog of these models, and then applying this to generate masses for the Yukawa couplings radiatively, like from together with the magnetic moment of the muon. That's the first part, and the second part is about it's much more phenomenological. It's about collider signatures of leptoquarks and future projections. For example, for future colliders like the muon collider and the FCCHH. So these 2 things.
I think these are all interesting. Okay.
Well, okay. Maybe I can go fast, and let's see if there are questions.
Okay, we can review.
Yeah.
Briefly
okay. Very good.
mention.
Yes, I'll just quickly mention these parts. Yeah. So here we are. So this is the work of Alanak and collaborators, where they looked into the solving the anomaly cancellation conditions, the anomalies of the anomalies of the quantum anomalies that come between when we introduce a U1x, a new gauge symmetry U1x with the standard model, the mixed ones, the self anomaly, and also the anomaly with the gravity. And there are basically 6 conditions that have to be satisfied for the charges. So we can imagine very general case where we consider 18 chiral fermions. So we introduce, in addition to the 5 gauge representation, we introduce right-handed neutrino, and all of these guys come in 3 copies. So in principle, we've got 3 times 6, which is 18 different fields, and in principle, all of them could have different charges. Okay, and this the thing that has to be satisfied are these, provided there are no extra chiral fermions, one needs to satisfy a consistent theory should satisfy these 6 equations. Okay. And so they basically come up with the atlas of possible integer charges. So integer charges, because this is a U1 symmetry, so it's compactified, it's S1, so it's the topology of the circle. And in this case, one can always rescale the gauge coupling, also because U1 it can be embedded into some, there's a hope that it can be embedded into some semi-simple to explain the quantization. It is then one can rescale the gauge coupling such a way that the smallest charge is 1. So one can always do this. So make the smallest charge 1, and then the other charges are integers, multiples of the smallest charge. And then they looked into how many inequivalent solutions are there in the range of all the charges between -10 and 10. So the standard model, this is the largest charge is 6. So it's the ratio of the charge of hypercharge of the left-handed quark doublets to the right-handed charge leptons. So this is 6. And here the range they consider is -10 to 10, and they look into inequivalent solutions. So clearly there is always flavor permutations. So what we associate to what. And other redundancies, and when they factor out these permutations, then they find a huge number of inequivalent solutions, about 21.5 million of those. And they provide the text file with these solutions that can be further investigated for model building, etc. So here, what we looked at, we wanted to focus on the lepton flavor catalog. And for simplicity, we impose quark flavor universality. So what does this mean? So we say that all the quarks have the same charge, and Higgs is uncharged. So this Higgs being uncharged is just, this can always be done. So there is always a freedom of field redefinitions of changing the coupling and the kinetic mixing in such a way to make Higgs having 0 charge to begin with. So under this assumption, we can write down the quark Yukawa couplings. So the quarks have the same charge and the Higgs has no charge. So Yukawa couplings can be written in the same way as in the standard model. There will be no extra selection rules there. And this requirement already makes a huge simplification of the parameter space of these U1 extensions. So out of 20-something million, we are down to only 276 models in the range of -10 to 10. So only this assumption of quark flavor universality. Now, what is interesting, what is very interesting is that the mu quark condition. So remember the first part of the talk where I charge a leptoquark under this lepton flavor group in such a way to have a charge to muons, but not to other leptons, and also not the diquark interaction, not to have proton decay. So it turns out that this can be achieved, that there is a choice for such a charge of the leptoquark to achieve the mu quark conditions in almost all of them. Out of 276, this can be done in 273. So somehow, like in this context, if you put leptoquark in the context of gauged lepton flavored universal extensions, this is automatic. These selection rules are sort of automatic. So there was nothing really special about the choice of the gauge group that we choose to do this paper. So there is plenty of other possibilities. Now we can further classify these solutions into the ones that are in the ones that where we can write down the Yukawa coupling for the leptons. So where where we can write down basically the lepton mass terms, the interactions with the Higgs. So where the charge of the left-handed guy is the same as the right-handed guy, although they could be different between different generations. They are different between different generations, but within a generation, the left guy can have the same charge as the right guy, and therefore we can write down 3-level dimension 4 Yukawa coupling, give it a mass. And most of the models are like that, 252 models. And this was the class basically of these previous models that I discussed, the one that can be parameterized by the B and individual lepton numbers. And finally, there is a chiral category where this is not the case, where we cannot write down a 3-level Yukawa coupling for the leptons, or at least for some of the leptons. And there are 21 inequivalent solutions. So this would be chiral charges for the leptons. Yeah. So my next example is about this class of models. So I think this can be useful in doing flavor model building. In particular, let's consider this model. So this is a viable charge assignment where we have different charges so you can see that there are different charges between the XLX for the left-handed lepton doublet and the right-handed electrons. So you see they are different, 7 and 8. And therefore we cannot write the Yukawa coupling. So we cannot write L bar Higgs E. So we cannot write 3-level muon Yukawa. So the dimension 4 muon Yukawa is forbidden because the charge is different. And then we can try to generate this after the breaking of the U1X symmetry. So let's say we introduce leptoquarks. Leptoquarks have this charge X. So this would be standard model quantum numbers. And this would be the charge of U1X. And in particular, there are 2 guys, the plus guy and the minus guy. So the plus one couples to the left-handed muons. So this interaction will give us the charge of the plus guy. So the charge of the plus guy will be basically determined by this interaction. And the minus guy will couple to right-handed muons. So it will have a different charge, but it can be computed from this interaction. So to allow for muon interacting with the 3rd generation quarks, with the top quark. And then the gauge symmetry will allow us to write another interaction between the scalars. So the leptoquark plus and the leptoquark minus could interact with the field phi, which breaks the U1 symmetry. So phi is responsible to break the U1 symmetry. And then the charge of phi is also fixed. So phi should have the negative, so the sum of the charges of these guys over here. So given the model, we can fix all the charges, we can choose gauge charges in such a way to have this situation. And then what happens in this case? So then we can draw these kind of diagrams. So here we can exchange the leptoquarks and the top quark in the loop. So this is the Higgs over here, and this is the scalar field phi. So notice that we can either attach a photon, in which case we get anomalous magnetic moment, or not. So if we don't attach a photon, so if we forget about the photon, this diagram here is just irradiative Yukawa of the Higgs to muons when phi gets a wave, when phi condenses. When we attach a photon, it will be anomalous magnetic moment of the muon. Okay? And in particular, notice that we have the same factors, because it's really the same similar loop. So the couplings and etc. We can make a correlation between the anomalous magnetic moment and the muon mass. So there is a formula between anomalous magnetic moment and the muon mass, which goes only in terms of the masses of the leptoquarks. And this is the if we translate the G-2 anomaly on the plane of taking the observed value of the muon mass and this anomaly from G-2, we can translate this onto the masses of the leptoquarks. We can predict the mass of the leptoquark, and it turns out to be in the range of several TeV, which is quite interesting. It is above the present exclusion limits. And yeah, so this only depends on the masses of the leptoquarks. Okay. Is there any questions about this?
This
Mr. Rees.
S1, S2, this linear combination of plus minus, or S
That's
plus,
correct.
S
So these
minus.
are the mass eigenstates. That's correct.
Mhm.
They are the mass eigenstates. So if they are degenerate, then it's roughly about 5 TeV if they were degenerate. But for example, they could be split. Maybe them being degenerate could be motivated by some extra symmetry, perhaps. But there is also a possibility that they are split, that one is rather heavy and the other one is light. If that's the situation, then maybe one is about, let's say, 4 TeV and the other one is about 10 TeV or so. But somehow we are always guaranteed to have at least one which is let's say within the FCCH age reach, not LHC for sure, but FCCH age. Okay.
This QS is the ion charge, right?
Sorry, say it again.
QS in the plot, this charge of QS.
No. So this is the electric charge of the leptoquark.
Electric charge. Yes.
So we choose this representation. So it's a doublet of SU2 with a hypercharge of 7/6. So the electric charge of the leptoquark is 5/3. This information might be interesting, let's say. Yeah, in the context of that's the guy which is running in this loop, because the top quark and the muon. Okay, very good. And then the last part is the collider physics. I'll go fast on this one. So the leptoquark signatures and the Drell-Yan versus B decays. So the leptoquark set hadron colliders. So we can they are colored, so they can be produced from gluon interactions, so in proton-proton collision, like for example the quarks, and then they would decay into a jet and a lepton, and then we would look for this in at the Atlas and CMS are already looking for these things. And in particular here, the production cross-section only depends on the mass of the leptoquark and the strong coupling constant. It doesn't depend much on the Yukawa coupling, so interaction of the leptoquark to quark and lepton. And therefore, the limits that we typically get are lower limits on the mass of the leptoquark, not very sensitive to the Yukawa coupling. On the opposite end, there is a correction of the leptoquark to the Drell-Yan. So we can exchange a leptoquark in the T channel and give a correction to the, so in proton collisions, we can produce dimuon pair, for instance, or dilepton pair by exchanging a leptoquark in the T channel. And this would give corrections to the tails of the Drell-Yan production at high energies. And then in between, we could, so this scales as linearly. So there is a linear relation between the coupling and the mass, because this is in the high energy limit, this would be just an effective semi-leptonic 4 fermion interaction. In between, there is sometimes some place for the production of a single leptoquark, either associated with the lepton, like that shown here, but also there is another mechanism where we just produce a leptoquark without a lepton that comes from the fusion directly of quark and lepton, relies on the lepton PDF inside the proton. And I will talk about it, I'll mention it, I'll not talk about it. Anyways, what is interesting is to look also. So these direct searches, sort of the pair production these ones, they are limited. So at the moment, the bounds are about 1.5 TeV, and that's it. The big next jump will be if FCCHH is built. FCCHH can go to 10 TeV, but for the moment, these bounds are sort of frozen, and LHC will not be able to make a lot of progress there. It just the bottleneck is the phase space. The heavier the leptoquark, we are producing 2 of them. We are paying a huge price on the phase space. So, but you have seen in many of my examples that actually this would not be enough. That in many cases that I had leptoquarks that are 3 TeV or 6 TeV or even 10 TeV and so on. And so we are really in the situation where leptoquarks are too heavy. And then perhaps we can consider looking into the Greljo, okay? And this is something that we proposed for the first time in this 2017 paper, where we can connect the correction to the high mass Greljo with these signs of new physics in these anomalies in the so potential signs. Maybe it's not new physics, maybe just a systematic uncertainty or something in B2S mu mu decays. And so in general, what we are talking about is a program where one studies semi-leptonic interactions, either in low energy physics, BEL-HCb, BEL-2, BES-3 experiment, or looking in the high mass Greljo, where we produce leptons, and together with possibly with the extra B jets and so on, and in high energies. So this is something that we are working on currently here in Bern. So we are extending the Flavio framework. So Flavio, you remember, is this Python package for global fits, which contains, mainly focus on like plethora of flavor physics observables and electric precision tests, etc. We are now adding the high mass Greljo, and this can be very important for certain class of models. And this is an example of the leptoquark, which is a muon quark, but which has minimal flavor violation in the quark couplings. So this construction is quite interesting to me from the phenomenological point of view. So this would be like a leptoquark. There are 3 leptoquarks for each generation of quarks. So it's a triplet of flavor in such a way that this interaction over here is flavor invariant. So you see, lambda is just a number, is one parameter. It's one dimensional, it's not a matrix. So this is a contraction in flavor space. So we've got 3 leptoquarks, which are in the SU3 of the quark doublet. And this Lagrangian is invariant under flavor, symmetry, and it doesn't give flavor violation. So we can give flavor violation through soft breaking by the mass term, which goes through the which is of minimal flavor violation type. Namely, we put here the top Yukawa. This would give us the splitting delta m square between the first, second, and third guy. And in the limit where splitting is switched off to 0, there will be no flavor changing neutral currents. So we need non-zero splitting in order, for example, to address the B2S LL, which is flavor changing neutral currents. And this is the parameter space where one can fit B2S LL. So this is the mass splitting between these top flavor, the leptoquark, and the light guys. And this is the mass on the horizontal axis is the mass of the light guy. So you can see here that the heavier the leptoquark, we need more mass splitting because we need more flavor violation to accommodate for the B physics anomalies. But it turns out that Greljo wants leptoquark to live here. So this is the preferred region by Greljo. Or in other words, Greljo gives a bound on the leptoquark to be above, let's say, something like 10 TeV, while B decays, they want the leptoquark to be in this range for a small mass splitting. So minimal flavor violation, actually there is a tension between high mass Drell-Yan and current B decays data. So in other words, you can say that this model cannot explain the anomaly because it will be in tension with the high mass Drell-Yan, or perhaps if this model is correct, then the measurement of the B to S mu is wrong.
Sorry,
Okay.
Can I try to understand this plot? The limit from
yes.
Drell-Yan limits this lighter mass, leptoquark mass, to be lighter, heavier than something.
Exactly. So this is allowed. So what is covered is allowed. So this is allowed. So it can be at least, so lambda is the coupling. But let's say lambda is 1. Lambda is this coupling over here. And let's say lambda is 1. So it means that leptoquark has to be at least, let's say, 9 TeV in order to be compatible with the bound.
I see.
So or heavier. It can be very heavy, and therefore there is no effect because the measurement in the Drell-Yan agrees with the standard model prediction. So leptoquark can be should be very heavy. It should not be lighter than this bound here.
I see. So
but in order to address anomalies, it has to be here.
I see. So then you are cutting when the delta m square equal to m square. You cut the plot where
yes. So I'm
ratio
considering
equals 1.
Yes. So I'm considering the case of a linear minimal flavor violation. So linear minimal flavor violation has this ratio less than 1 in such a way that I can expand in the top Yukawa. When this is much bigger than 1 or order 1, then this symmetry is not SU3, is actually SU2. It's broken. So it's badly broken. So the breaking parameter is order 1. So actually this is not MFV anymore. This is something which is called generalized MFV or U2 flavor symmetries. So U2 from the work of Barbieri and Isidori. And those are actually okay. So if I were to extend this plot, eventually there would be a little parameter space. So here the statement is really about minimal flavor violation. So minimal flavor violation is in tension with the data. Linear minimal flavor violation.
Okay.
And this statement is quite generic also for like a Z prime model. So if you, this is something that we are working, this is a work in progress, and soon we will, for example, if you, consider, we have one example also in this paper here that of a Z prime, which has the MFV and is excluded by the Drell-Yan. Okay, so the point is that these guys couple to valence quarks. So here you see there is a leptoquark which couples to up quark, so up type guy, and therefore it will give you correction to the valence, so the production from up PDF. So UU bar giving you L plus L minus. If you don't couple to valence quarks, but you just couple to a B quark, then there is a B PDF suppression, and then you are okay in these U2 type models. Okay. And then I also have this part about future colliders. I don't know if maybe it's so it's a discussion about muon collider versus the FCCHH, and then we looked into, maybe I can just show the plot. So this is the plot. So what we are doing in this plot is the following. So we are taking this S3 leptoquark, which gives a 3-level correction to B to S mu mu. So I showed this diagram already. So there is a B quark going to muon with the exchange of a leptoquark, and then strange to muon. So it's a 3-level correction to B to S mu mu decays, where we have these flavor anomalies. And in particular, they tell us that the product of the leptoquark couplings, lambda B mu to lambda S mu, is given in terms of the leptoquark mass. So the heavier the leptoquark, the larger the coupling we need to explain the excess. And this is the relation. So now in this 2D plot, what we are doing, so we have a mass of the leptoquark, versus the coupling to the B. And for each point in this, parameter space, we are fixing the third coupling. So you see, there are 3 couplings. So we fix this coupling. For each point in parameter space, we fix the third coupling. So in particular, the region which is shown in gray is excluded by perturbative unitarity. So if we require very heavy leptoquark, or if we require one coupling to be much bigger than the other coupling, then basically we have perturbativity. Couplings cannot be bigger than something. So the criteria that we use is that the resonance, the width, the total width of the resonance is less than 25%. So that's our sort of qualitative criteria. And so this defines our parameter space. So you see, the heaviest leptoquark, which satisfies perturbativity, is about 50 TeV, if you want to explain this anomaly. And now we have all sorts of different bounds. I don't want to go into details, but this is, for example, what high Lumi LHC can do. The white parameter space is completely open. So the collider cannot, high Lumi LHC will not able to enter the white parameter space. Then you see FCC can enter very much a lot of this parameter space. So this over here is the pair production limit, while the one from the side is the Drell-Yan, high mass Drell-Yan limit. You see FCCHH can enter, but it cannot fully cover this part. And this is how a 3 TeV muon collider will do, and a 10 TeV muon collider will cover completely this model. So to be fair, here one should also consider in this parameter space this resonant leptoquark production, where one produces leptoquarks directly from a lepton PDF. So lepton PDF inside the proton was recently computed by Giulia Zandarighi and collaborators, and we have done a POHEG plus Herwig implementation in NLO QCD plus QED together with the group of Giulia. We have made this Monte Carlo to do this study. And this is what we sort of find is that basically for FCCHH, so this is FCCHH, pair production can go up to 12 TeV, while this resonant leptoquark can cut into parameter space. So for large couplings, this resonant leptoquark can really go further into the parameter space. So some part of parameter space over here might be accessible to this mechanism, which goes by this diagram. That's it. I'm very sorry for being over time, and probably I prepared too many things. So these are the conclusions of my talk. Yeah, I won't read them, and I'll make the slides, of course, available. And thank you very much. And I'm here if you have further questions.
Thank you very much. Thank you very much for your interesting and kind talk. So now open to questions and comments. Are there any questions or comments? Can I ask?
Yes, please.
Yeah. It seems that the leptoquark that interact with the first generation are quite constrained. So
Yes.
Is there any possibility that theoretical possibility that only the second and the third generation interacting leptoquark are preferred? Yeah.
Yes. So we usually call these like U2 flavor structure.
Oh, I see.
So where we couple.
Mm-hmm.
So if there was something, I don't have anything to write, but maybe maybe I can explain it. Well, I had it in the first part of my talk.
Oh, I see.
So here, in this model, just a second. Wait. Where I had the plot. Yeah. So here, Yeah, so eta is the coupling to quarks. So this is the coupling to the first generation, second, and third generation quark.
Yeah, you said that.
Yes, so this would be this U2 flavor structure where a leptoquark couples dominantly to the third generation, like the Higgs. So it's a scalar like the Higgs, and then the couplings to the light generations are suppressed a la CKM. And these kind of models are okay. And while the model that I showed in the end, where leptoquarks couple, there are 3 of them and they couple strongly to, one of them couples strongly to the first generation. This is in problems with the high mass Drelian constraint. But these ones are not, they are okay. So this parameter space is allowed.
Oh, yeah, right. Yeah, thank you very much.
Actually, the model that I showed in the end for the projections, this one, also this is the bound from high mass Drelian. So the bound over here, and this is very weak bound because this guy does not couple to down. It just couples to B and S, but not to down.
No down.
Yeah,
right. Oh, thank you very much for kind explanation. Any other questions or comments?
I have a very naive question. In the beginning of your talk, you said the leptoquark can be scalar or vector, right? So I wonder the scenario for the vector leptoquark. Is it maybe the story totally changed or?
Well, it does. So there are plenty of models, and I worked on some of these models. The most I think the most interesting one for me is the Patti-Salam-like extensions of the standard model. So probably you've heard of these 4-3-2-1 gauge models. So you extend the standard model by SU4, and there in the breaking of SU4 there will be literally the Patti-Salam leptoquark, which is a vector and which it's a gauge boson of this gauge symmetry, and that one is very popular these days, and that one can for example also address the other type of anomaly, which is RD and RD star in B to C tau nu transitions. So actually I have a backup slide for the vector leptoquark model. So the story is pretty much similar. So if you use vector leptoquark, so I just used scalar for simplicity in this talk, but most of the story can be done also for the vector leptoquark. So here, this is the plot for the vector lepto. You can recognize it's quite similar. But the vector leptoquark, they have this additional complexity that they are massive vectors. So one has to specify how to get their mass. So there is some gauge symmetry. If they are fundamental fields, that should be a gauge symmetry, and they should be gauge bosons of a gauge symmetry, which is spontaneously broken. Or if they are composite, they should be some composite resonances, etc. So there is much more involved model building to be done with vector lab, which exists, of course. But on the pheno side, also all this story that I've told about gauging a flavor, lepton flavor U1 can also be done with the leptoquarks. In the paper, we have one model where we really have like this 4-3-2-1 model. So the vector leptoquark SU4, SU3, SU2, U1, together with the U1 of the lepton flavored, and we are embedding this in SU5. So basically, vector leptoquark will be a muoquark, will carry a lepton number. It's a bit more involved, but these things can be repeated.
Sorry, maybe I don't understand the beginning point. So in the scalar leptoquark case, you consider the U1x and scalar leptoquark charged and the U1x. But in the vector leptoquark case, the vector is also associated to the U1x. Can I?
So they have to be then unified. They have to come from the so the vector, it comes from SU4. So let me very quickly I will show you for the just very quickly. What's the time in Korea?
7:40.
Oh, I'm really sorry for keeping you out from your dinner.
It's okay.
It's a
Yeah,
great talk. I think we can spend more hour.
I can show you very quickly what
Thank you.
what I mean by this. Stop sharing and share this. Yeah, so it's a model which is here. So basically, so it's basically SU5 gauge group. So there is an SU5 gauge group, and then what happens is that SU5 breaks down to it will break down. So the color will be embedded in the diagonal of SU3 times SU3. So we have 5, 3, 2, 1. So the color will be the diagonal of 3 and 3, 3 from 5 and SU3 prime. And the hypercharge is diagonal of U1 5 and U1 prime. And then we've got basically we can do this breaking of 5, 3, 2, 1 gauge group to the standard model times U1 mu minus tau. The gauge symmetry U1 mu minus tau. And in this breaking, the 24, which are the gauge boson of the SU5, you see there will be this guy, which is this guy over here, which will be a leptoquark, and it will also it will be a leptoquark, and so this guy over here, but it will also carry a lepton flavor under this gauge, under this extra gauge group. So when you break further SU2 to U1 mu minus tau, you will get two guys. One will be mu quark, the other one will be the tau quark. It will be a gauge boson, which is so this kind of construction. They are a bit more involved, but they can be done.
Okay, thank you. But the discussion of the discrete symmetry is specific for the scalar leptoquark, right? So okay.
Oh, okay. The discrete symmetry we have not studied for the vector leptoquark. Yes. Yeah, indeed, that's correct. So yes, we have not studied. I suspect that something similar might happen there, but yes.
Okay, thank you.
Sure.
Any more other questions or comments? So if there are no more questions, then we should properly close this question and answer time. So let's thank Professor Greljo again.
Thank you very much.
Thank you for a nice talk. Yeah.
Well, thank you for letting me go over time. I usually don't have I think yes, I usually don't have so much time to. But it was nice to say all these things that I've been working on for the last few years.
I think that is very nice. I think we have nice connection to unification, and then just the low energy point of view, people have been working on G prime a lot, but it's good to have such a nice connection to unification, and also I think I like that discrete symmetry a lot. So
okay, thank you.
Protect proton from decay. So, and the connection to the thermal leptogenesis scenario. So that's also interesting. Okay, so I think the Admir Greljo, probably we may have a lot of questions also from students, but it's getting late. So thank Admir Greljo again. And also for attending, for all of you for your attendances. Okay, hopefully we can see each other again.
Yes. Well, see you. If not,
so you said you are moving to Basel in the end of January.
That's correct. Yes.
See. So can you come back? Can you come to Korea in February?
No, yeah, I did this. So I'm starting a position there, and yeah, so first year probably I won't be moving a lot, but
okay.
but yeah.
So congratulations for your
Thank
new
you.
position. So when we go visit your place or son, maybe we can go to Basel.
Yes, please. Yeah, I would be happy
country,
to.
right?
I would be happy to host you for sure. Please, yeah.
Yeah, sure. Yeah, let's keep in touch. And if we have any questions, then we can contact. I think the student feel free to contact you.
Yes. Yeah. Absolutely. Yeah.
Okay. Thank you very much.
I am actually looking for a postdoc next, just to advertise in Basel starting next fall. So, yeah, I'm very happy to receive applications.
I see. Thank you.
Right.
Okay. So hopefully you can send me your talk file such that we can revisit your talk slides and ask questions.
Okay. Thank you very much.
Okay. Thank
Have a
you.
nice